thank you everybody, and I'd like to start by thanking the organisers of the conference for the opportunity to talk to you all this morning. My name is Ian Engelbrecht. I'm presenting some work that I've been doing with Mark Robertson at the University of Pretoria for my PhD work. And the actual purpose of this presentation is to give you a gratuitous sales pitch for our session on invertebrates today. This is not something that happens very often at a conservation conference where you have a whole day-long session just to talk about invertebrate conservation. But I think you'll all agree that invertebrates are a critical part of biodiversity. They make up a significant proportion of biodiversity. They play a really critical role in ecosystems. But a lot of our conservation activities tend to ignore invertebrates, which is something that we'd like to address. So the purpose of this session today is to showcase some of the invertebrate conservation work that is happening in South Africa, to try and promote that to the conservation community more broadly, and to try and see an increase in interest in invertebrate conservation as a result. And we're actually very lucky today in that we've got some real live taxonomists that have come to this conference, and you can come and see them in this session. And they're going to be, these are people who actually dedicate their lives and their time and are incredibly passionate about discovering and describing biodiversity. They're really doing the foundational work that we as conservationists, to produce the information that we as conservationists need to use. So I'm just going to tell you a little bit more about some of the challenges involved with invertebrate conservation, and I'm going to illustrate it with the work that I've been doing in Gauteng Province. About 8 years ago I started working for Gauteng Nature Conservation. Gauteng is the most pressured province in South Africa in terms of development. We've only got about 50% of our vegetation in the province that remains natural, and it's highly fragmented. So prioritizing areas in Gauteng for conservation is quite important. And we had a conservation plan in the province that was developed using the C-Plan software, which was really important in a lot of our decision making. And trapdoor spiders were a very important part of this conservation plan. And when I arrived there, they said to me, "You need to take over this work with the trapdoor spiders." And what was happening was, so this map over here just shows you some of the areas in the province where trapdoor spiders were seen to be an important part of the biodiversity. And whenever we got EIA applications within these areas, specialist consultants had to go out and do surveys for trapdoor spiders to figure out whether they were actually there, and that would have implications for whether or not the development would go ahead. This was generally a positive thing, but we started to get some red flags in this process. We started to have difficulties identifying some of these trapdoor spiders, and we started to find species that were supposedly quite range restricted, very far away from where they were supposed to be, which indicated that maybe some of our thinking about how we'd included these in the conservation plan wasn't quite correct. It was obvious that further work needed to be done, and so that's what I got busy with. And what I started to do was to try and look at the taxonomy to assess how good the taxonomy was, and part of that was to try and assess the total number of species that are actually out there relative to the number that we know about and that have been described. To do this, I went through all the primary taxonomic literature, I pulled out all the locality records, and I used the Chow-1 species richness estimator to try and estimate total species richness for groups of taxa, where singletons were taken to be species which had only been recorded at one locality, doubletons at 2 localities, and then obviously you've got the total number of described species. And as you can see from this graph, in most cases we only know about a relatively small proportion of the total trapdoor spider diversity. This is just a total of what you saw on the previous graph. There are about 163 described species of trapdoor spiders. This is in southern Africa, and I estimated that there were about 366. It could be a lot lower than that. The confidence intervals on these estimates are quite wide, but it could also be quite a lot higher the average is that only about 44% of the species have been described. And from the work that we've been doing, the surveys that we've been doing, backs this up, because at almost every single site that we sample, we will get at least one or more species of trapdoor spiders that we haven't seen before. What makes the matter more complicated is that these animals have extreme sexual dimorphism. This is the same species of trapdoor spider, an adult male on the left-hand side here, and an adult female on the right-hand side. The females are these really sort of stockily bodied animals with very short legs, which is an adaptation for living in these burrows that they make, which I'll show you in the next slide. Whereas the males, when they mature, they develop these elongated legs and all kinds of structures on their front legs and on their pedipalps for mating with the females, and they go walking in search of the females, which is why they need those nice long legs. The difficulty, though, yeah, it's the other way around. The difficulty with this is that females are highly morphologically conservative, so different species will look very similar to one another. In fact, you often can't tell different species apart based on the females, and all of the important characteristics for identifying a species are on the males. And in a lot of cases, you'll have species that are described only on a male or only on a female, and it's difficult to actually match them up and know what you're looking at. So we need to go out and sample spiders and try and collect as many as possible to resolve the taxonomy, which is a very nice idea, but these guys like to hide. So they make these little burrows in the ground, little tubular burrows, which they line with silk, and they cover that burrow with a little lid made of silk so that it's perfectly camouflaged with the surrounding soil. You literally cannot find these things. Occasionally, I'm sure everyone's seen a trapdoor in the wild, but most of the time most of the time you're lucky to see a trapdoor in the wild. There are many, many more trapdoor spiders out there than what we actually realize, because they hide themselves so well. To make it more complicated, the males, which we need for taxonomic purposes, are only available to be sampled for very short periods of the year. They mature at the beginning of the breeding season, and they come out and start walking around looking for females. The females eat them, other things eat them, or they just die of exhaustion. And you only have literally a couple of weeks or maybe a month or two in which you can sample these spiders. So we actually use pitfall trapping to sample trapdoor spiders. This is just some examples of photos from the work I've been doing. We set out these traps. They're 1 litre plastic tubs which we put in the soil with plastic drift fences in between, so that when the males are walking between the traps, they bump into the drift fences and walk along and fall into the traps. But this is incredibly labour-intensive work. We've worked out that you need about 200 pitfall traps at one site in order to sample these things. That's the team of people that helps us put these pitfall traps in. And you need to operate them under very specific weather conditions. The males only come out after rainfall, so you have to be there at the right time. And you also have to operate these traps throughout an entire season or an entire year, because different species are active at different times of the year. So in order to get everything that occurs at a particular site, you need to do quite a lot of sampling. So it's very labour intensive, and it's very costly to do this. So I have been doing this for several years and been having a great time doing it. I've got some publications out of it and some popular press articles and things like that. But the important thing about it is that the picture that we have of trapdoor spider diversity in Gauteng Province now is very different to what we had when these things were in our conservation plan and we were using them for EIA decisions. So just as an example, we had 5 species of armoured trapdoor spiders in our conservation plan. They belong to a genus called Galliosoma, and they were all thought to be relatively range-restricted Gauteng endemics. From the sampling that we've done, it looks like we've only actually got 2 species, and they're quite wide-ranging. We get them at most of the sites that we're sampling. So species that we thought several species that we thought were important important doesn't actually look as though they are all that important. Conversely, we had a species of corklid trapdoor spider, which called Stasimopus robertsi. We thought it was relatively widely distributed. Wherever people went, they dug out females, and oh, this is robertsi. And it was thought to be something that was unimportant. But what we found is that it's actually a whole group of species where the females are identical to each other. Wow, 5 minutes. I thought I had 20 minutes. Okay, all right. So what happened there was that it turned out that the nominal species, the one that we thought wasn't important, is only confirmed from 3 localities in Pretoria. 2 of those are like 1914, it was seen there. We've only collected it at 1 locality in Fairy Glen Nature Reserve, right in the middle of Pretoria. So it's probably quite a threatened species. So this led to the question, would it be possible for us to effectively conserve trapdoor spiders without knowing anything about trapdoor spiders? And I think that's an important question for invertebrates in general. So, and what this question evolved out of was the work that I was doing trying to select sample sites for this survey. And I came across a method called environmental diversity, which was originally proposed in the literature for selecting, for prioritizing areas for conservation. They said that for most taxa on Earth, we don't have complete distributional information. Most of the area prioritization procedures that we have available to us, like MarkSan and C-Plan and things like that, require distribution data. So these guys proposed this method that said, well, let's try and do it without good distribution data. And the concept is very simple. It's going to be intuitive to most people, is that if you try to protect areas that are environmentally as different to one another as possible, you should also capture a large number of species in those areas. It's based on the assumption that turnover in species composition is related to turnover in environmental conditions. And it sounds like a really nice concept. So this is just to illustrate it very quickly. If we were doing a conservation planning exercise and we had to choose, for example, 2 new conservation sites, let's say we had 3 sites that were already conserved and a whole lot of potential candidate sites, we could measure environmental variables at all of those sites and plot them in an environmental space. So those are the same sites plotted along axes of temperature and rainfall, and the obvious ones to choose, because they are most environmentally different, are those 2 sites over there. And if you can plot them back into your geographic space, and then you know which areas you want to conserve. What this requires is some kind of measure of distance between sites. And just using the simple example again, what you simply do is scale your axes to 0 and 1 so that you don't have any kind of magnitude effect on your distances, and you just calculate Euclidean distances in that environmental space like that. And you end up with a matrix that looks something like that. The distance between site 1 and site 2 is some other distance, site 1 and site 3. And this is basically the bottom half of one of those sites by sites distance matrices. And these are just some equations that you use for working out how many distances you will have and all the rest of it. But in reality, we're probably dealing in most examples with numerous sites. These are the centroids of all the quarter-degree grid squares in South Africa, and this is the scale of the analysis that I will be showing you in a moment. And it's about 2,000 sites that we're looking at here. If you plot them on those same axes that I showed you, temperature and rainfall, you effectively get a picture of what the environmental space of South Africa looks like along those 2 gradients. And then you plot them in geographic space again to see what you're looking at. So this sounds like a really great idea. What we found is that probably the biggest strength with it is that it's incredibly flexible. Because you're using a derived measure of distance between sites, you can formulate that distance in a huge number of ways, using different combinations of environmental variables, weighting environmental variables. And you can even use community dissimilarity. If you've got a complete community matrix, you can incorporate species richness information, so you bias selections towards towards areas of your space where there's high species richness and high turnover between sites. And it sounds really fantastic, but the big question is, does it work? So we set out to assess this in South Africa using some really fantastic distributional data sets that we have for the country. I think we have some of the best biodiversity distribution data sets in the world, and the ADU allowed us access to their data sets for some of their more recent projects. And we also generated a set of artificial species distributions to get away from things like sampling issues and biogeographic effects and that sort of thing. And what was interesting, our artificial distributions were effectively just randomly located environmental envelopes, and so they're scattered around in the environmental space. They're variable sizes, but when you plot them, you get quite an interesting species richness pattern like that. So we compared 4 methods for selecting sites: random sampling, stratified random sampling, where you divide environmental gradients up into strata and then sample randomly within those, a geographic grid-based sampling approach, I think the battery's dying here, and ED. Now you do that for a whole range of sample sizes up to the total 2,000 sites that you have, well, in South Africa, that's what we were using, quarter-degree squares. And I'm just showing you the first 600 sites here, which corresponds to about 30% of the total area. And what we see, and this is with the artificial species distributions, and what we see is when you select sites using environmental diversity, that curve, which is the diamonds up at the top, comes out quite distinctively above the other methods. So this method is performing significantly better than other methods for recovering species diversity. That solid line at the top is what you get if you use actual complementarity using a program like MarkSan or CPlan. So you're not getting as much as you do if you have the actual distributions, but it's pretty close. And just to show you the empirical examples quickly, that was on the artificial data sets. It should have worked here, and it did, which was great. But it still works with butterflies. That curve is coming out above the others, and also working quite nicely with frogs. With reptiles, the pattern is a little bit less clear, and it seems like reptiles are in general quite difficult to capture with this kind of thing. But it's still significantly better than random, and marginally better than selecting sites on a geographic grid. So what's really important about this is that the studies that have been done to date suggest that ED doesn't work. There's been a long debate in the literature. It was proposed by some guys in Australia, and it's been evaluated by people in other parts of the world. The guys who have evaluated it say that the underlying assumptions are flawed. The guys in Australia are saying, yeah, but you're doing it wrong. And every time they do a new assessment, they say, you still did it wrong. So we spent a lot of time trying to figure out how this thing actually works, and we actually got a positive result, which is really interesting. And moving forward, we'd like to see how far up we can actually push that little line of diamonds towards that black line. All right, so that's it. Thank you very much.